Today we're going to talk about microcontrollers and design patterns. So some of this will be supplemented by a material that's on the website and is worth taking a look at, and there's also some supplementary readings there as well that can help you learn this. But the idea is we're going to go over the basics of microcontrollers so you know enough about the interfaces to look at data sheets and be able to tell if a sensor will work with a microcontroller that you've got. And we'll also talk about the common software design patterns that we use when we're writing code for microcontrollers, especially state machines, as that's one that we use in the laboratory quite often. So first we'll go over some of the interfaces, and a few of these would be PWM or pulse width modulation, serial and parallel communication, I2C or I2C, SPI, and then we'll talk about some software things like timers and interrupts, and structures like state machines, and also a polling structure. So this is a really quick overview of, as normal, a pretty broad range of topics. Each of these we could devote a lot more time to, but the idea is that you know that they exist and know the basics of them and where to go look for more information when you need it, because there's a lot of information that you're not going to be able to fully grasp until you've dealt with it. For example, when we talk about I2C communication, the way to really learn it is to have a problem and spend a lot of time troubleshooting that problem and fundamentally understanding how the protocol works. So pulse width modulation is up first. It's the idea that we have a square wave of some frequency and we change the duty cycle of that square wave, and we use that to control something. This is used to control servos. We also use it to kind of fake out a digital to analog converter. The higher the duty cycle, the higher the output voltage after we filter this square wave would be, so we could generate a voltage between 0 and whatever the top voltage on our square wave is. So at the top here you see a 50% duty cycle, which is equal amounts of time on and off, and 75% duty cycle is on more than off, and 25% duty cycle is of course on for a very short amount of time. Doing this in the Arduino interface, we can do things like dim or brighten an LED. This is a simple program that will do that. It connects an LED to pin 9, and then it fades, so it gets brighter and dimmer and brighter and dimmer over and over again. The key command here is analog write. You see in the loop analog write, LED, which is the pin, and brightness. That brightness is a value between 0 and 255, and that changes the effective output voltage, or what changes the duty cycle really, on pin 9. So if you were to hook an oscilloscope up to this, you would see the duty cycle increasing or decreasing. And I would encourage you to type this in. It's just a few lines really. Type it into the Arduino IDE, upload it, and watch what the LED does. Also, it's worth noting how they did the reversing the direction. Where down there, fade amount equals minus fade amount if the brightness was going to be less than 0 or greater than 255. That's a clever trick. That's something that you'll see quite a bit. As I mentioned, we also use pulse width modulation to drive servos. So here you see we use the servo object in the Arduino IDE, and we just attach a servo, in this case on pin 9, to this object myServo that we created, and then we can say myServo.write and give it a position between 0 and 180 degrees, and it computes what the correct pulse width modulation, the frequency, and the duty cycle should be, and goes ahead and sends that off to your servo. So this abstracts away you needing to know exactly how the pulse width modulation controls the position of the servo. Something that's worth learning, but it's also not the main point here when you're trying to drive a servo in your code. Another interface that you'll run into quite a bit is a parallel interface. This transfers many data bits at once. So you can see here we have an interface that's transferring a complete byte, so 8 bits. And what happens is on the device that is sending the data, you set all of those bits. You could do it at once, or you could wait and do them individually, or you could shift it in, and then you use a clock pulse to tell the receiving device, okay, clock in all of this data at once. So since we're transferring, in this case, a full byte, in many cases more than a full byte at once, this is a really fast interface, but it does require more wires because we're having a wire for each bit that we're transferring plus the clock line. You might remember seeing these on old printers and other things that we would connect to our computers. They were these big DB25 plugs. There's a picture of one here. And so you can see how many conductors are required to do this. It's a big connector, it's a big wire, and it is a little bit more to break, but you do get that speed gain. On the Arduino, there are two ports. There is an 8 and a 6-bit port that you can set. You can see in this code I'm saying port D equals and port B equals. That lets me set all of the outputs on that port, the digital outputs, at once. And in this case, I'm using it following the style of W2AEW on his YouTube channel to draw, in this case, the Penn State PSU on an oscilloscope screen by making digital to analog converters through an R2R resistor network. But the idea is you can do parallel communication with your Arduino if you need to. Serial interfaces are one that you'll run into maybe a little bit more commonly, and you might say that serial is outdated and nobody uses it, but I'll remind you that USB is the universal serial bus. We're fundamentally in serial transferring data 1 bit at a time. So you can see that we've got a byte going across here from the output to the input and a clock cycle on every one that's synchronizing, saying, okay, there's a byte, or there's a bit here, clock it in. Next bit, clock it in. Next bit, clock it in, and so on. There are interfaces that do not use a clock line. They agree on a data rate, and through something called a UART, Universal Asynchronous Receiver Transmitter, they can coordinate this serial communication, and that is commonly what's done when you're talking, for example, to your Arduino. And in that case, you agree on the data rate or the baud rate, but you also have to agree on how the packets are going to be formatted. Now, there's normally a start bit, because these packets could be coming at any time since there's no clock line. And then there's the data, and there's a parity bit, which is a basic form of error checking. You can set this to either show you whether there's even or odd numbers of ones in the data section of the packet. So it's basic error checking. It doesn't get around near everything, but it's a good first order check. And then there are 1 to 2 stop bits on the end generally to say the packet has been completed. Now, between serial and parallel, like always, there's a trade-off. Serial you can think of as this really wide highway where we're moving a massive amount of information, or cars, but it's expensive to build and sometimes difficult to maintain. The smaller serial bus is more like this country road. We can put cars through it, in this case, one at a time, but it's a lot easier to deal with than this large parallel highway and costs a lot less to build. With the Arduino, you can do serial communications pretty easily. You can see here that we start in the setup method. We have this serial.begin 9600 saying that we want 9600 baud, and then we're reading an analog port, storing it in a variable sensor value, and then this serial.println or print line lets us send that data back to the computer through a serial interface. In this case, we want to use the println because we want to print the sensor value and then go to the next line and print the sensor value and go to the next line. So each value is on a new line and it's easy for us to read. If you take the ln off, it would just string them all together on one line. And when you're sending data back, you'll often use a combination of prints and println or printline to format the data how you want. Another interface is SPI, Serial Peripheral Interface. You often hear it called SPI. It's a 4-wire bus, and it is pretty high throughput. The idea is there's a clock line, SCK, serial clock. There's a line called MOSI, which is master out, slave in, a line called MISO, which is master in, slave out, and then a line that's called SS or CS for slave select or chip select that tells the device I am talking to you specifically. Down below there's a diagram of the basic way that this interface works. You can see that on the rising edge of the clock, in this case, we're reading the data that's on MOSI. So this is going to the slave device. And then later on the rising edge of the clock, we are reading data back onto the master from the slave device. And the slave select line is pulled low for the duration of the communication to tell the chip, yes, I'm talking to you. You can put multiple devices on the bus. So here you see they're sharing a clock, MOSI, and MISO lines, but each device needs its own selection line. So this does take a lot more pins on your microcontroller, which can be a problem on micros that don't have a lot of pins or on projects where you have a lot of devices. Another thing you'll see sometimes are devices that can be daisy-chained together. So here you see the MOSI line goes from the master into the first device, then out into MOSI of the second, out into MOSI of the third, and then MISO comes from the last device all the way back to the master device. I would say this is not nearly as common of a configuration, though. On your Arduino, there is a library that helps you do all this. You can see the function listing at the right, and if you go to the Arduino website, you can click these and get the full details on all of them. It's relatively easy to write your own way to talk to various devices using this library. And all of the interface bits about, okay, we're going to read on rising clock edge, and then we're going to do this, have been abstracted away for you, but you'll probably have to go in and do some troubleshooting at some point, so it's helpful to know how it works. Another interface is called I2C, the Inter-Integrated Circuit interface, or I2C is how you'll hear it commonly referred to. It only has 2 wires, and you can have multiple master and multiple slave devices. And these wires are the data, SDA, and clock, SCL lines. It is a little bit more complicated than SPI because one line, the data line, is carrying data in both directions. So you can only have one device, you can talk master to slave or slave to master, unlike on SPI where both of those communications could happen concurrently. Here you have to wait. You have to say, well, you tell it an address, in this case a 7-bit address, then read or write. So this says, I am talking to this particular sensor on the bus. And then that sensor says, okay. Then you send it a command, and you can either read data back from it during that, or you can send it a command. So these packets, there's a lot more overhead. We're having to say, okay, this device address, read write, then do your transaction. The next time you want to talk to that device, this address, read write, do your transaction. So it's not as fast, but it has a greatly reduced number of wires, right? There's no selection line, and you only have the clock and the data lines to worry about. But it is at the expense of complication and speed. The library to do this is called the wire library, and you can see the functions here. Once again, I encourage you to go to the website and check these out. They're pretty easy to use, and I've not had any problems using this library to talk to a wide variety of sensors. So now we're going to get a little bit into the code side of things. When you're writing code in the Arduino IDE, you're really writing pretty much C++. It's very important when you're writing code to break it up into functions, not just have this one monolithic loop block. You want to break things out so you can reuse them, and so they're easier to maintain and easier to see the flow of the program. This is the breakdown of a function. You see that at the beginning, we have to declare what the function is going to return, in this case an integer. You can say void, but I encourage you to always return something, even if it's just a 1 or a 0, to say whether the function succeeded or not. Then a function name, in this case my multiply function, and the parameters that we're going to pass to it, in this case an integer x and an integer y. Inside, I declare a value or an integer result that's going to store x times y, and then we return that result. So what happens is we would call this function, the code inside it would run, it would return the return value, and our code would pick up where it left off. Also make sure you remember the curly braces and the semicolons at the end. That's a common mistake when you're getting started. So if we create that multiply function, this is what it would look like. And you can see in the loop that I have some variables I, j, and k. And then I call multiply function. So I'm saying k equals multiply function I, j. That means pass 2 as x, 3 as y into multiply function, and whatever it gives me back as the return value, stick that into k. And then I print that to the terminal and I wait half a second. So in this case, the terminal is going to print 6 over and over and over again. Not a very interesting program, and we're implementing functionality that already exists in this case, but you can see that functions could be very useful to break your program up into reusable, maintainable chunks. So now let's look at a couple ways that we can interact with the outside world. Let's say that you have a package coming. You ordered something off Amazon, maybe you ordered something from SparkFun, and you want to make sure that you know exactly when it arrives so you can tear the box open and start working immediately. Maybe it's a couple days before your semester project's due, and this has the last pieces that you need. Well, you could just go to the door every few minutes and open the door, look, is the package there? No. Close the door, go back into your house, sit down, do something for 2 minutes, then go back. That's not very efficient, but you would know within a couple minutes of when the package got there. That would be called polling. You're repeatedly checking for a condition or for an event, just over and over and over. One problem would be, let's say something else was going on that took a while, like you were in the shower. Well, you might not get to that polling bit for a while. So the package could be sitting there outside. So polling does have some disadvantages in terms of if you're somewhere else in the program that takes a while, you might not get to poll very often. Another way would be using what's called an interrupt. And this would be like having the delivery notifications texted to you on your phone, which you can do. So you would be just working away, you could be doing whatever you want, and you would get this buzz in your pocket and some kind of sound. You look at your phone, it would say the package has been delivered. You go to your front door, and there it is. Now, the key is it stops you from whatever you're doing. If you are a computer or a microcontroller and there's an interrupt, that interrupt stops you dead in your tracks, and you go take care of it. You can also see there could be some problems with that from a program flow standpoint. But let's look at polling. So in this example, we are going to have a button, and we're going to make an LED reflect whether the button is pressed or not. So you could do this without a microcontroller, of course, but it's a nice simple example. So we set up the LED as an output, and the button is an input, and we are reading the button. If the button is high, we turn the LED on. If the button is low, we turn the LED off, and then we go back and read the button again. And we do that over and over and over as fast as we can. That's an example of polling. And you can see that the program can't do much else, or the button might not be that responsive. So you're kind of wasting a lot of resources and a lot of cycles there, maybe even a lot of power. But the interrupt would allow us to handle the event. And I'm going to show you why they can be difficult to debug and kind of the anatomy of an interrupt. So let's say the interrupt occurs. Be called an IRQ normally, an interrupt request. The computer is going to save where it is. So it says, I'm here in the program. And then it calls the interrupt service routine, or ISR, and runs it. These interrupt service routines should be very short. They shouldn't take a ton of time, or who knows what's going to be going on in your main program that you're missing because you're hung up in an interrupt. Then after the interrupt service routine is completed, the program is going to go back to where it was. It restores its state, and there's a question mark there because not all processors do this, and it doesn't always work right if something happened in the interrupt that could affect the way that the main program was flowing. For example, on your Arduino, it should go back and pick up where it left off in the main program, but you'll see if you use interrupts that they can cause some really squirrely behavior that can be really difficult to debug because it depends on when in the main program the interrupt occurs. So you might have to try causing the interrupt at different places and see if you can reproduce the behavior. This is an example of using the attach interrupt function. In this case, we're attaching interrupt 0 to the pin interrupt service routine, which is down below. It's a function. And we're saying that we want to only deal with a change. So whether it goes from 1 to 0 or 0 to 1. In the interrupt service routine, it reads the button and it writes that to the LED. That's all it does. And you notice in the loop, there's nothing there. So we could put other code in the loop that would be running. And then when the button changed state, it would call the interrupt service routine, handle it, and then go back to whatever is running in the main loop. If you're doing, not using this attach interrupt is a wrapper that makes things easier for you. This is what it would actually look like if you're enabling interrupts and then using the external interrupt 0, saying we're going to trigger it on a falling edge, and then this ISR with the interrupt 0 vector on it down below as a function. This is what it would look like in a more traditional programming environment. But the Arduino environment kind of wraps that up and makes it easier for you to get used to, but you shouldn't be scared of this. You just have to look it up, and it gives you a lot more versatility. We can also use a timer to generate an interrupt, so we can say every so many clock cycles, which is every fixed amount of time, fire this interrupt service routine. That can be very handy for events that have to occur on a fixed time base. They must occur, but it introduces lots of places where things could go wrong in your program because you are regularly interrupting the normal flow of the program. This is an example of how to use a timer. Again, I would refer you to the documentation because it can get complex relatively quickly, but as long as you read it and make sure you understand what you're doing, they are not that bad to use. So another design pattern that you'll see a lot, and this is one that I use quite a bit in equipment, is the state machine. And we use this in laboratory equipment just a ton, because you think about it, we go from one state to another. We start, say we collect data, then we average it, then we plot it, then we write it to a file. We do something like that. For an airplane, you could think of states being takeoff, cruise, landing, as maybe the very basic states. But you can get as granular as you want with this. Some people are splitters, some people are lumpers, where some people have a few big states. Some people have many, many small states that are each not doing a whole lot. The ideal is somewhere in between. I tend to err personally a little bit more on the splitter side, just because that's how I think, and I like really small, compact states that are easier to maintain. And if I decide to refactor or change the functionality, I can probably string them together in a little bit different way and not have to change what each state does. We would show this with a state transition diagram. This is not using UML or Universal Markup Language. A lot of times we show start with a solid filled dot and end with a solid filled dot with a circle around it. And the idea is each arrow is a transition, each circle is a state, and those transitions can be conditional. So you can go from start to state 1 and say that you are waiting on a button press to go to state 2. And then as soon as you're done with state 2, you come back to state 1. And maybe after you do that 10 times, you go to state n in this case. Just a random example. When you implement a state machine, there are really 5, I think, fundamental things. An outer while loop, so you keep coming back to the top over and over again, seeing what state you're in and then going and doing that. There's an inner case structure that these are more LabVIEW terms, but they apply to, well, as you'll see, C as well. This inner case structure says, okay, if I'm in this state, I'm going to do this. If I'm in this state, I'm going to do this. If I'm in this state, I'm going to do this. The initial state is crucial. A lot of times people will design a state machine and forget to set the initial state. So they boot up and nothing happens, or it goes to a random state, which could be even worse. Often the first state is initialize, which does things like set up the inputs and outputs, do a little bit of housekeeping, figure out what mode we're in, and then go to that state. So the initial state is often initialize. They're similar but different. For example, you could have the initial state be a state called startup. And then at the end of each state, it needs to know what the next state is. So you need to set the next state. This could be done in some kind of queued manner. This could be done just with an enum or something like that, where you say the next state is going to be collect data, let's say, or write to disk. And then every state machine needs to have a shutdown state. I am a firm believer in this because things will go wrong, and the shutdown state should be the error condition, or if the user presses like a stop button, the machine should shut off. Or if there's a critical error, you don't want it to just keep running with this critical error or go to some random error state. You want to make sure that things are safely shut off. In the lab, this is especially important. For example, make sure hydraulic pistons are locked, or make sure X-ray sources are turned off, or make sure a shutter to a neutron source is turned off, things that could actually harm you. So this is an activity that we did during the lecture with an ultrasonic tape measure. Here we've got an ultrasonic pinger that sends out a ping, and it then times how long, or we can time how long that ping takes to return from, say, bouncing off a wall. And from that, and knowing the speed of sound, we can figure out how far away something is. You can see in the photo somebody has taken an LCD and keypad shield, put it on top of an Arduino, put this ultrasonic ranger at the front, and they're showing a distance of 5.8 inches to something. So I will put on the website a diagram of the state machine that maybe I would come up with for this. But we can think about states already. We would have an initialize state. Then we might have a transmit state, a listening state, a calculate state, a display state, a shutdown state. Maybe you could lump some of those together, like calculate and display, or transmit and listen could be called measure. So there's kind of the splitter versus lumper mentality. Another architecture, and this is easier to show with a LabVIEW-like diagram than to show you in code, which is why I'm doing this, but each of these gray things, gray boxes with arrows, are while loops. And then there's a queue. The idea is there's two while loops that run concurrently in this case, a producer and a consumer loop. This is harder to do on embedded unless you have multiple cores. I would say it's more often seen in desktop control software. But the producer loop would do something like, say, we read a bunch of sensors, and we're doing it 100 times a second. It would read the sensor, put the data into the queue, then go back, and the next time it needed to do it, read the sensor, put the data into the queue. Then the consumer loop down at the bottom, running at whatever speed it can, pulls data off the queue, processes it, so it could display it, it could write it to a file, it could do some calculations with it, and it pulls data off as fast as it can. Now, if it's too slow, eventually the queue will become full or you'll run out of memory. But what's nice is, say that you have pulsed data collection, where you're doing very rapid data collection for a little bit, then you slow down. Well, this lets the consumer loop have some time to catch up. So they can run at different rates, and you don't have to slow down the producer loop by doing all of the analysis, plotting, etc. in it. So the assignment that y'all are going to work on is doing an Arduino stoplight. So it's a stoplight with a left turn light in this case, and a button to represent a car in the left turn lane. It should work like a normal stoplight. Instructions are on the website. And there are, you should use good design. You should use a state machine architecture. I have shown in class, and we'll post on the website after this is due, a basic state machine and how you could implement it in C. So you should use something like that. It should be functionalized, and it should be well documented, and it needs to actually do the job right, and it needs to have a shutdown state. When you're looking up the switch statement, you should see a default. So you could have switch, multiple cases, and then default, and that would be something bad has happened. Let's go to shutdown. For the in-class portion of the day, we're going to design a state machine for an X-ray diffractometer. There's a video on the website of one of these working if you've never seen it. The idea is, on paper, we're going to draw with the circles and the arrows and the transitions, a state machine for this X-ray diffractometer. There is on the activity page what's called a user story. These are common ways that we specify portions of software, where we say this is how the user is going to interact with the machine. They're going to go up, they're going to open a door, they're going to click a button, they're going to wait for something to happen, and you need to make sure, in this case, that it is safe. This is an X-ray machine. It could fundamentally hurt someone. So there would definitely need to be something like, if somebody opens the door and it's running, it goes to a shutdown state immediately. So have a look at that activity on the website, pair up if you'd like, and make sure that you turn in a copy of your state machines. I highly recommend that you use the UML, Universal Markup Language, symbols for this.